In this video lecture, I want to show by example how one can derive the impulse response and the unit step response of a LTI system that has been described by its differential equation. And we're going to do this by example, and the following example is described by this LDE. It will be of the form a linear operator L operating on the output Y equal to a linear driving operator LD operating on the input U. And so we'll have a U of t applied to our system, and I'm going to write H of t as the way we're going to describe it. That's what we're after, producing an output Y of t. Specifically, the system is Y double dot plus 3 I'm sorry, not y double dot, y dot. Y dot plus 3y is equal to u dot plus 1u. We can put this in the linear operator form as d plus 3 operating on y of t equal to d plus 1 operating on u of t. Now, we have previously seen that the form of the impulse response is the same as the homogeneous response, because other than at the moment t equal to 0, where the impulse driving the input is non-zero and undefined, for all other time the input is 0. So if we put in a delta function to our system, we'll get the h of t out, and basically this is equal to, or it's undefined at 0, and then it's 0 for all other time. So what we're really solving is d plus 3 so the characteristic equation is s plus 3. Okay, that's determined by L, what's operating on y. And so we have a root at minus 3, which gives us a homogeneous response, which will be the impulse response as well, of some constant times e to the minus 3t times the unit step. So this right here is my unit step, 1 for all time greater than 0. This C1 is unknown. Okay, this is what we need to find. Now, what's different in this system from the most basic is that there's a driving operator. There's actually a derivative of u plus u. So to solve such a problem, in other words, to find the unknown coefficient C1 to basically complete the impulse response, we need to define an intermediate system. So we're going to define an h hat of t, where it's going to be defined as y of t is equal to LD operating on h hat of t. In other words, d plus 1 operating on, not h hat, sorry, y hat. Y hat. Okay, so it's kind of an implicit definition because we're not expressing y hat equal to, instead we're expressing y as a function of y hat. But this is handy because what we're going to do is plug it into the linear differential equation. What does it give us? We have L operating on y, okay, but actually we're going to replace that with LD y hat. Right, this here is y equal to LD operating on u of t. Now, L and LD are commutative. They're linear operators, and we can commute them. So what we have on the left side now is LD times L operating on y hat, or we could say LD operating on L operating on y hat. equal to LD operating on U. Okay, which is satisfied if L operating on Y hat is equal to U. So let's solve. So here's our approach. Let me rewrite this. Our approach for finding h of t, the impulse response of the original system. Find h hat of t corresponding to the system L operating on y hat equal to u of t, and then solve h of t is simply going to be equal to LD operating on h of t. Right? This is because we've defined y hat as having the relationship with y of y equal to LD operating on y hat. Okay? So that's our approach. So here we go. So we have d plus 3 operating on h hat is equal to the delta function. Okay? And of course this, so we're already going to have the form that h hat of t is going to be some constant c, let's see, I'll call it c2 at the moment. Maybe I'll call it c1 hat. c1 hat times e to the minus 3t times the unit step. Okay, that's the easy part. Now, how to find the initial condition, or how to find c1 hat. Okay, integrate the LDE, this one here, over 0 minus to 0 plus time. So it'll become apparent why we do that, or why that would be useful. So we'll have y hat dot plus 3, I'm sorry, h hat dot plus 3 h hat dt equal integral of the impulse function dt. On the right, by definition, the area under the impulse is 1. And since we're crossing 0 where it fires, it will integrate to 1. On the left side, what we have is we have the integral of d h hat dt, all of that times dt. So we're taking the antiderivative of the derivative, plus 3 integral of h hat of t. Okay, so now this first integral simply becomes the dt's cross, and we'll get integral of dh hat evaluated from h hat 0 minus to h hat 0 plus 3 times, and now we think, okay, if we're integrating the second integration, if we integrate over 0 time, 0 plus to 0 minus to 0 plus is an infinitesimally small time. So unless what we're integrating is infinite, that integral will amount to 0, and that's what's going to happen here, because h hat is not infinite at within that range of 0 minus to 0 plus, and so this will be 0. This leads us to h hat 0 plus minus h hat 0 minus is equal to 1. But h hat at 0 minus is 0 because the system is causal. Alright, if h hat 0 minus was not 0, then it would mean that we have a response in the system before the input is actually applied, because the input due to the impulse actually occurs at time 0. So we'd have a non-causal system. Okay, so now we have our result that we were looking for, the initial condition, that h 0 plus, which we can say loosely, okay, loosely that h hat of 0 is equal to 1. Now we can use that to solve for c1 hat. Okay, so now we can bring this down and we can write that h hat of t is equal to 1 e to the minus 3t times the unit step. That's not our final answer, so let's just bracket it. That's h hat. That is the response due to for a system L operating on y hat equal to u of t. Alright, what we really need is we want h of t, which recall that's going to be LD operating on h hat of t. This is d plus 1, now operating on e to the minus 3t times the unit step. Okay, so what does that give us? It'll be the derivative with respect to time of e to the minus 3t times the unit step plus e to the minus 3t times the unit step. Now to evaluate the derivative of this expression, we're going to do the chain rule. So it will be minus 3 e to the minus 3t times the unit step plus that's ugly, plus e to the minus 3t times the derivative of the unit step. Derivative of the unit step is the impulse. And we'll have plus e to the minus 3t times the unit step. Let's clean this up. We'll have h of t is equal to minus 2 e to the minus 3t times the unit step plus e to the minus 3t times the delta function. But I can clean this up a little further, or simplify it, by getting rid of the weight in front of the impulse. Okay, since the impulse function is non-zero only at time 0, then the importance of this exponential is really simply at what its value is when time is equal to 0, which is 1. And so this is 1 at t equal to 0. So we'll just replace it with 1, because for all other times the delta function will be 0. So that is our impulse response. Okay. Now let's find the unit step response. Find unit step response. And we're going to solve this two ways. Okay. First way is two methods. Okay, two methods. One, using h of t, and two, from the LDE. Okay? So in the first method, we have, if you put in an impulse and you get the impulse response, then if you put in the integral of the impulse, which is equal to the unit step, then you get the integral of the impulse response, which is the unit step response. So all we need to do is evaluate the integral from 0 to t, and we'll be specific and say 0 plus. From 0 plus of t to t of minus 2 e to the minus 3 tau times 1 times the unit step plus the delta function. Okay, d tau. So what do we have? We'll have 2/3 e to the minus 3 tau. Now I should say this right here is not needed. Alright? It's not needed because the limits of integration are from 0 to t. We're not going negative. Okay? So it'll be 2/3 e to the minus 3 tau evaluated from 0 to t plus, now we're going to take the integral of the delta function and we'll get the unit step. Okay, and I shouldn't do, I'm sorry, that shouldn't be 0 plus, that should be 0, or actually specifically 0 minus. Let's see what we get here. When you take the integral of the unit step, you will get, integral of the impulse response, you'll get the unit step and evaluated from 0 to t. Okay? So, and I'm going to say 0 minus. So we have 2/3 e to the minus 3t minus 2/3 plus unit step. Okay, and actually, so I need to add a unit step here to be clear, right? Because the first term is not defined. It's going to be 0 for time less than 0. Right? So yeah, and then the second term I have the unit step 1 of t minus 0. Okay, now we can put that all together, and what we have is 1/3 plus 2/3 e to the minus 3t, the whole thing, times the unit step. Okay. Now let's plot that. Actually, let's go back and plot h of t. H of t was this decaying exponential, which starts at minus 2 right here, and then there was an impulse. Maybe I should have done it in, okay, in yellow. Okay, that's h of t. Now redraw this, and what we have here for the unit step is, let's see, at 0 it's going to be 1, and asymptotically when the exponential goes away it will be 1/3. Okay, and so the response decays down like so. Okay, now let's verify our result that we found for the unit step response by actually solving this straight from the LDE. So we're going to use, remember we said two methods, using h of t, and now we're going to do it using the LDE. So method 2, g of t from the LDE. So the LDE is, we have d plus 3 operating on g of t is equal to d plus 1 operating on 1 of t. Okay? Now this is a little tricky to solve, and the reason is that there is a derivative on the driving side. Okay, there are two ways to solve, well, at least two ways to solve this. One is to recognize that if you take the derivative of the unit step, you have an impulse. And so what's happening here is we actually have an impulse plus the unit step. And if we have an impulse right at 0, then that's going to set some initial conditions. And it actually will turn out that that impulse at times, fired at 0, will actually cause the initial condition of g of t being equal to 1. Okay, but that might not be apparent. And we, in general, we may not have a driving operator that's just simply d plus 1. So the alternative way of doing this is to define a system d plus 3 g hat is equal to the unit step, and then we will define g of t as being equal to LD operating on g hat of t. This is exactly analogous to what we just did when we were finding the initial conditions for h of t. So let's solve for g hat. So g hat has a particular solution. Let's say it has a homogeneous solution that is simply going to be some constant, and I'll say k1 e to the minus 3t. All right, that's because the characteristic equation being s plus 3. The particular solution is going to be equal to, well, it's going to be a constant. I'll call it k2. You can plug that in. We'll get d plus 3 operating on k2. Right, that's coming from here. Equal to 1. This is for time greater than 0. Right, the unit step goes to 1. So what do we have? 3k2 equal 1, k2 equal to 1/3. So therefore we have g hat of t is equal to 1/3 plus k1 e to the minus 3t. Right, all of that times the unit step. Now, what is the initial condition on here? I'm sorry, not gh, that's g hat. Let me correct that, g hat of t. Yep, that's the complete solution. Complete solution. G hat at time 0 is going to be equal to 0. Okay? One of the things is when you're looking at the impulse response, or asked, okay, here's a system, find h of t, it is assumed that it's a zero state response. It does not incorporate any other initial conditions. So since we're solving that same problem but now with a different method, we assume that g hat of 0 is equal to 0. And that leads to k1 must therefore be equal to minus 1/3. Okay? So let's rewrite this. G hat of t is equal to 1/3 times 1 plus e to the minus 3t. Oh, sorry, minus. Okay, minus. All right. And therefore, g of t is equal to LD g hat of t, which is equal to d plus 1 operating on g hat of t. What does that give us? We'll get 1/3, 1 minus e to the minus 3t, right? I should put in my 1 of t here. Okay. So that's the plus 1 term. Okay. And then we have plus d. Okay. Let me write this on a new page here. Let's just go to new page, because it's going to be long. We have g of t is equal to d plus 1 operating on 1/3 times 1 minus e to the minus 3t times 1 of t. All right, that's going to be d operating on all of this, okay, plus 1/3 1 minus e to the minus 3t times 1 of t. So now let's distribute this derivative. What we'll have is, when we take the derivative, we'll do chain rule. We'll have 1/3 times, it'll actually be times 3 e to the minus 3t, right? That'll be the derivative of the first term, plus the derivative of the delta of the unit step, which is going to be the delta function, times 1/3 times 1 minus e to the minus 3t, right? Plus this whole thing. Now let's look at this right here. The delta function is non-zero only at time 0, right? But at time 0 we get 1 minus 1 equal to 0 at t equal to 0. So therefore this term vanishes. Okay. Now you might say, well, it could be a finite value, right? An infinite times a 0, but the thing is, it lasts for a 0 amount of time. Okay, so if it is a finite value, it lasts for 0 time, and so unless it's actually something that's infinite that lasts a 0 time, it has no real existence, if you will, practical existence. That might not be the mathematical term, but that's what we'll go with. Okay, so now we have a e to the minus 3t plus minus 1/3 e to the minus 3t plus 1/3. And we arrive at 2/3 e to the minus 3t, oh, and this is all times 1 of t, plus 1/3 times 1 of t. Now, does this agree with what we found before? Let's go up. Okay, so right here we had 1/3 plus 2/3 e to the minus 3t, and yep, okay, they agree. Checkbox, they agree. Okay, so you can pick which way you want to do it. In my opinion is I'd rather go straight from the impulse response if I can. All right, so we have at this point finished our task of finding the impulse response and the unit step response to this first order system that included a driving operator driving the input